we have to move to the next presentation, which is actually the last before our coffee break, marking a half point of today's symposium. The next one is by Professor, and apologies for the pronunciation, by Byung-Dae Park with the Department of Wood Science and Technology at the Kyungpook National University.
Thank you.
The topic is recent progress on the formaldehyde emission from bonded wood products. So now we move from the nano and micro area to macro area. So Dr. Park, the floor is yours.
Thank you very much for your kind introduction. So let me share the screen first. I'm very happy to be a part of this IUFRO special session of the World Wood Day Symposium. Today I'm going to talk about the recent progress on the formaldehyde emission from the bonded wood product. I guess you know the formaldehyde emission has been an issue for a long time, since in the mid-1980s. But I'm going to tell you a little bit about news stories on the formaldehyde emission issues. Let me give you a brief outline of my presentation. I'm going to talk about the interaction, which include carbon dioxide storage and the bonded wood product, and the formaldehyde emission, the urea formaldehyde resin. And then I'm going to move to the raw molar ratio UF resin, which also discuss about the property of the UF resin and the crystallinity of UF resins. And then I'm going to talk about the modification of the UF with the nano clays. And then I'm going to tell you about the performance of these modified UF resin, and then come down to the conclusion of my presentation. You know, this, everybody knows the wood contains the carbon dioxide. As this graph shows the net carbon dioxide and life cycle emission for different materials, which include wood, minerals, and the metals. As you see here, all the metals has much higher the carbon dioxide life cycle is emission, and then mineral is a little bit small. But all the wood product, which includes sawn timber, softwood plywood, birch plywood, laminated veneer lumber, particle board, hardwood, softwood, so they are all the negative numbers. That means they are containing the carbon dioxide in these products, which may be help the mitigating the climate change in the future. So why we are still using adhesives? As you know, we are limited the large diameter logs, and then we have a lot of the small diameter logs available for the making product. In that case, we need adhesive to bond them together. Small pieces bond them together. Big product like glue lamps, cross-laminated timbers, plywood, particle board, MDF, those kind of these things. So where the wood adhesives comes from, I guess everyone knows most of the wood adhesives are based on formaldehyde resins. They are petrochemicals. And first, I want to focus on the UF resin, which is a product of reaction between formaldehyde and the urea. This is mainly responsible for the formaldehyde emissions. So as you may know, this UF resin has been synthesized in 1884 by Holzer, a long time ago, and then it's commercialized, and it's been used more than 100 years. The wood product industry still use UF resin. Why? Because UF resin has a good performance. They have good the adhesion strength, and also fast curing. They are inexpensive. It's cheaper, and also colorless. But there is some disadvantages. One of the critical disadvantages for formaldehyde emission, so everyone knows. And also, UF resin bonded product has a low water resistance and the low durability. So that's why UF resin bonded mainly used for the interior application. Today, I'm going to mainly focus on the formaldehyde emissions of this product. So as you know, the formaldehyde emission goes very long time. As you see here, emission goes to more than 500 days, which is much longer than compared to other volatile organic compounds. And then there are many different ways or different approaches to reducing the emission, including the synthetic control. I mean, how you could cook the resin, and you may play with the formulations. And also you can have low formaldehyde urea molar ratio. And also sometimes you can use scavengers, such like a dry urea or dry solution, or you can use post chambers like ammonia chambers. But today, I'm going to mainly focus on the low molar ratio resins. So what the people are doing is to reduce the molar ratio to have a low formaldehyde emission. And then I'm going to tell you what's happening when you have a low molar ratio resins. What I did is I prepared a different molar ratio IUFRO resins like this. And then we test the various properties. First of all, the gelation time is increasing, and also delta H, which is the energy to cure the resin, it's increasing when you have a low molar ratio resins. That means that when you reduce the molar ratio, you have lose reactivity and need more energy. But when you have the low molar ratio resin here, you have a less emission, that's for sure. And also you have a less fully formaldehyde in the resin after cooking. So that means you have less emissions. And what I did is we prepared the films of the IUFRO resin and then cured at different temperatures, depending on different molar ratio resins. As expected, higher molar ratio, much higher the hardness, and compared to the low ones. Low ones usually have the lower hardness. And then we also did, sorry about that. Narrow indentation, I did also narrow indentation at the same films, and then we have the low hardness for the low molar ratios. That means when you have a low molar ratio, you have a low emission, but you have soft material at the end. And also, if you have the low molar ratio resin, you have the low additions and internal bond strength, and also higher thicker swelling. That means if you have a low molar ratio, you don't have the good properties. And then we look at the hydrolytic stability. I mean, how these the IUFRO resins are hydrolyzed at the different molar ratios. So what we did is we prepared the different IUFRO resins depending on molar ratios, and then cure them and then ground them in the powder, and then we have different particle size, and then put them in the hydrochloric acid for artificial hydrolysis, and then we measure mass loss and liberate the formaldehyde concentration after the hydrolysis. Surprisingly, low molar ratio has much less mass loss. That means it is much more recent hydrolysis, which is very contrasting the one we know. And the formaldehyde concentration of the similar trend. That means the low molar ratio is a little bit recent hydrolysis. And then we question why, and then we look at the XRD, X-ray diffractions. As you see here, the low molar ratio resin 1.0, 1.2 is much more crystallized compared to higher molar, which are amorphous. And then we calculate the crystallinity of these resins depending on the molar ratio. About 1.0 molar ratio has about 48% crystallinity. That means almost half of them is crystallized, the other half of them is amorphous. And also the crystal size also increases when you have low molar ratio resins. And then we also look at the morphology of the cured IUFRO resins by preparing the two parallel plywoods using the adhesion between them. And then we look at the split them half, and then we look at what was going on the cured resins in the wood. And then we found the different types of the crystal structures in these resins in wood. And also we did look at TEM. This is high molar 1.6, this is 1.0. 1.0 low molar is much more dark spherical particles. I believe these are responsible for the crystallinity of these the low molar ratio resins. And then we look at these resins with XRLD, with wood, without wood. They're pretty much same crystal patterns, and with wood, a little bit smaller size. And then we also did the electron diffraction, which gives a different number of the rings, which means these crystals are polycrystals. I mean, different types of crystals are combined together at the same place. So, and recently we did the AFM and the TM to look at this morphology cured resin. As you see here, right-hand side, AFM shows pretty much the lamellar crystal structure for the low molar ratio resins. We also confirmed the lamellar structure with the TM. However, the high molar ratio resins are pretty much amorphous, showing the compound of AFM and the TM. So that means the most low molar ratio has crystal structures in lamellar types. And then we also look at what was happening in the liquid resin, and then we look at the XRD for liquid resin. So as expected, the low molar ratio has about 28%, which is smaller than the cured one, but still they have the crystallinity. And then we also luckily found the crystal particles in the liquid resins. That means most of the crystals in the liquid, it moves to the cured resin, and they aggregate into much bigger and more crystallized, high crystallinity. And then we look at what was happening in here, and then we look at the FTIR and the proton NMR. And then what we found is this is NH and this is the carbonyl groups. So compare the red dot line is 1.6 and the black solid line is the 1.0 lines. So there are some different shift of these wave numbers. That means there is the NH as moving because of hydrogen bond between linear molecules in the low molar ratios. It's the same thing in the carbonyl groups, and also we have the same thing in the proton NMRs. So the shifts are that the chemical shifts are moving up here and over here as well. So this means this resin has a hydrogen bond, which is what. And then we came out with ideas like this. The high molar ratio resins like this, a little bit of branch polymers, but when you have a low molar ratio, it's pretty much the linear molecules because the formaldehyde is kind of the cross-linkers. They are less formaldehyde means they have less cross-linkers. So what I thought is we have this kind of the hydrogen bond between linear molecules, the amino group NH, to the carbonyl groups. This is a component with FTIR and NMR, proton NMRs. So how are we going to do this? What should I do? I mean, what I'm saying is the current low molar ratio is quite different to those resins used in the first few decades. I mean, the crystal structure in low molar resins are responsible for the poor resin. What I'm saying is low molar ratio resins has crystal structure instead of the building three-dimensional structure, which gives a strength in the polymer. That means low molar ratio has a poor cohesion in bond lines. So the idea is very simple. That we try to modify the low molar ratio with nanoclay. As you know, nanoclays are layer structures like this, and that they have a 1 nanometer thick like this, and also they have exchangeable ions, which is a sodium cations between layers. And once you mix with the nanoclays with the polymers, some of the polymers that sit between the nanoclay layers, or some of the nanoclay layers are exfoliated. So the idea is we want to try to exchange this ion, sodium ion, with the different ion, which is bigger, which is means the copper chloride. So we have the sodium ion cation here. We exchange the sodium cation ion with the copper ions because copper is bigger, radius is much bigger than the sodiums. And then what we expected is we have little bit of distance, a large distance between the nanoclay layers, and then you expected the IUFRO molecules sitting between the nanoclay layers. And then we add the TMI bentonite. That means the transition methylene modified the bentonite, which is nanoclay, modified nanoclay, and mixed with the UF resins. I mean, actually, it's cooked in the kettle. When you have 5% the modified resin, you have much faster curing detected by DSC. At the same thing, but detected by DMA much faster than the control. What was happening here? That means we explained that the copper ions are hydrolyzed and then they release the protons which accelerate the cure of the UF resin. That's why the modified resin have faster curing. And then we also look at the XRDs. And as you see here, the control, and this is 5% modified nanoclay. Compared to the others, the 5% modified nanoclay resin almost amorphous. That means most of the crystal structure is gone. And then as you look at this, the rectangular bars here, this is right here. That means some of the nanoclays are intercalated or some of them is exfoliated, which prevent making a crystal structure in the resins. So, and then we calculate the crystallinity of these modified resins depending on the modified nanoclay levels. As you see here, crystallinity pretty much decreased at 5% modified nanoclay. And also we calculate the crystal linking density of these resins using DMA at different isothermal scanning. As expected, the cross-linking density of this modified resin increases at 5%. That means they are making a three-dimensional structure instead of making the lamellar crystal structures. So right-hand side, that is the schematic diagram of what we thought. So we have lamellar layer structure of the nanoclay and also linear molecules of the low molarity resin. And then these have a hydrogen bond between them. Once mixed with the modified nanoclay, which is a little bit larger distance between layers. And then some of the UF resin molecules are intercalated between the layers of the nanoclay, and some of them is exfoliated. So that means some of the hydrogen bond in the low molarity is blocked, or some of them is prevented, which gives a three-dimensional structure, which means I expect it gives a higher cohesion strength, which will obviously improve the adhesion at the end. So this is what I got from three different wood-based products, plywood and the particle board, MDF. So first here is the tensile shear strength of the plywood, which increased about 56% at 5% modified nanoclay. At the same time, we have formaldehyde emission decrease about 48%. And the particle board is also increased adhesion and the internal bond strength. And also formaldehyde is reduced about 32%. And MDF has almost double the internal bond strength. And also they have about 36% of formaldehyde reduced. So here's the conclusion of my presentation. I would say the low molarity has gives low emission and high crystallinity at the expense of the poor adhesion. Liquid and the cured UF resin with a low molarity shows lamellar crystal structures, which are believed to be responsible for the poor adhesion. And the modified UF is the modified nanoclay simultaneously at the same time improve the formaldehyde emission and addition of plywood, particle board, MDF because of the better cohesion compared to controlled resin. And these improvements could make a contribution in extending the use of wood-based composite product in the future, which may be help in mitigating climate change in the future. Before I finish, I want to share the one information which is going to be held in Korea in the end of the September, which is BioComp 2021. I'd like to invite you ever to come to this conference. Possibly the meeting will be the hybrid format with combining the online as well as offline. But but I don't know, maybe it depends on the COVID-19 situation at the end of this September. With that, thank you very much for your attention. I would be happy to answer any question if you may have. Thank you.
Thank you, Professor Park. We have time for one question. Sometimes it's difficult to come up with questions. If you have any later on, please feel free to contact Professor Park. Thank you again for your great presentation. We're going to have a short meeting right now, about 10 minutes long. So if you don't mind, rejoin the session in about 20 after your time.
Thank you.
Thank you.